I want to use this video not only as an example of node analysis, but also of a review of how we deal with the math that comes about from mesh analysis. It always ends up with a system of linear equations, where you've got an equation for each of the node voltages. So we've got this circuit here, and as you can see, there's three critical nodes. There's one here, and then this bottom one here. So we're going to call that our reference where V equals 0. We'll call this V1, we'll call this V2. We're now going to go ahead and write the two node equations associated with it. So the current leaving this node going in this direction is going to be V1 minus 10 divided by 1 ohm, plus the current coming down here is going to be V1 minus 0. We're not going to write that minus 0 very often, but we will this time. V1 minus 0 divided by 5, plus the current leaving this node going that direction is V1 minus V2 divided by 2 ohms, and the sum of those three currents has to equal 0. So this is at node 1, and then we'll do it at node 2. Node 2 here, the current leaving going to the left is going to be V2 minus V1 divided by 2 ohms, plus V2 coming down here through the 10 ohm resistor is going to be V2 minus 0 divided by 10 ohms. And then we have this 2 amps coming in, entering as a negative, so it'll be minus 2. The sum of those three currents equals 0. Now, let's just point out that both of these equations involve a term associated with a current in this 2 ohm resistor. The node equation here at V1 has the current leaving V1 going this direction as being V1 minus V2 divided by 2. And the second node equation has the current leaving V2 going in this direction as being V2 minus V1 divided by 2. Notice that those two terms both describe the same current, only in opposite directions, and so they differ by a sign. This one is the same as this times minus 1. Alrighty, now, how do we go about solving this for V1 and V2? Well, I'm going to show you at least a couple of different ways. One way is to realize, and this is nice when you have nice clean denominators, which in homework and test problems you frequently do, but in the real world seldom. Let's just realize that this equation has as denominators 2, 5, and 1. So if we multiply both sides of this equation by the least common denominator of those three terms, which would be 10, we can then clear the denominators. And that then gives us, we've got 10 times this term here is going to be 10 times V1 minus 10, plus now 10 times this term right here. I've got 10 divided by 5, so that leaves me a factor of 2, plus 2 times V1 minus 0. Let's not write the minus 0. Plus 10 times this term right here. The 10 is the factor of 2, and the 10 is canceled by 2 here, and we're left with a factor of 5 multiplying V1 minus V2, and that then equals 0. And similarly, we can do down here, the denominators are the same, so the least common denominator is going to be 10 here also. When we do this, we get 10 times this term here, the 2's cancel, and it then gives us, we had to draw arrows saying here, coming on over here because it's the same equation, just a different form. So 10 times this, the 2's cancel, and we're left with 5 times V2 minus V1, plus now 10 times this term, the 10's cancel, and we're just left with V2. And then we have 10 times a minus 2 is a minus 20, and the sum of those terms equals 0. Now, let's clear this up. Combining terms, we've got V1 times 10 plus 2 is 12, plus 5 is 17. And then we've got plus V2 times, let's see, I've only got one V2 term here, and it's got a minus 5 multiplying it. And then as far as constants that I'm going to bring to the other side, I've got 10 times a minus 10. That's a minus 100 on the left side, which when I bring it to the other side equals 100. And the second equation, gathering terms, I've got V1 here. In this equation, I've got only a minus 5V1, so it'll be a minus 5 there, plus V2 times, I've got 5 plus 1 is 6, and that then equals, I've got a minus 20 here that I bring to the other side as a positive 20. Alrighty, we've got two equations in two unknowns. How you choose to solve that depends on what skills you've got and what things you've got available. Well, one way would be to do this by hand. And so let's solve this using a technique that they teach you in college algebra. It's known as elimination. And to do that, we're going to multiply this equation by 6, both sides of this equation by 6, and both sides of this equation by 5, because when we do so, we'll get a negative 30 V2 term in this equation and a positive 30 V2 in this equation, which when we then add those two equations together will eliminate the V2 terms, and we're able to solve for V1. So we're going to multiply this equation right here times 6, and we're going to multiply this equation right here times 5. And when we do that, we get 6 times 17, that's 102 V1, 102 V1 minus 30 V2 equals 600. When I multiply this equation by 5, I get minus 25 V1 plus 30 V2 equals 100. Now, when we add those two equations together, the V2 terms cancel, and we're left with 77 V1 equals 700, or V1 equals 700 divided by 77 is 100 over 11. Now take that V1 value and plug it in and into any of the equations that have V1 and V2, and you can then solve for V2 is equal to 120 over 11. Now, in this period, end of story there. Another way of doing that using technology, and you might as well get used to using your calculators on this, because frequently when doing node analysis, you'll run into either third order or fourth order systems, which are 3 equations and 3 unknowns, or 4 equations and 4 unknowns. So let's just show how we would solve this using our matrix solver or the solve equation, or the solve function on your calculator. The solve equation, of course, the solve function, of course, you just type in these two equations and let it solve for x, v1 and v2. Another way is to use your matrix solver, which would consist of forming these two matrices. The coefficient matrix, which is 17 minus 5, and 6, times, of course, your variable vector v1, v2, equals 100. And so if this is your A matrix, and this is your B matrix, the matrix of V1 and V2, we can write that. Let me just write it up here. I'm running out of room. We could then write the matrix V1, V2 then is equal to A inverse times B. Okay? Alrighty. Let's just do one more way of dealing with this kind of equation here, where you've got all sorts of fractions. The one drawback to node analysis is that you do have to work with fractions. Fractions are not the end of the world. You've got to get good at using and working with fractions if you're going to be an engineer. So another clever way of doing this is to simply not bother getting common denominators the way we did over here, and multiplying by, let me say that again, not worry about eliminating the denominators by multiplying by the common denominator. Just take it as it comes. Let's look at this first equation here and combine the V1 terms. So I'm going to get all the V1 terms together. I'm going to factor out the V1. And here I've got V1 over 1, which when I factor out V1, I've got 1. Plus, now here I have V1 over 5. I factor out the V1, I've got a 1/5. And here I have V1 over 2, which when I factor out the V1, I'm left with a plus 1/2. Those are my V1 terms, plus V2. Now I only have one V2 term. That's a negative V2 over 2. When I factor out a positive V2, I'm left with a negative 1/2 here. And then over here on the other side, I'm going to just go ahead and bring my constants. I've got negative 10 divided by 1, so it's a negative 10 on the left side. I bring it to the other side as a positive 10. Now doing the same thing for the second equation, first of all I'm going to combine my V1 terms. I factor out the V1, and here I have only one V1 term. It's got a negative 1/2 plus V2. I've got V2 over 1, or I'm sorry, V2 over 2. So factor out the V2, which leaves a 1/2. Plus I've got V2 over 10, so factor out the V2, and I'm left with a 1/10. And then I've got this minus 2 here that I bring to the other side as a positive 2. Okay. And once again, this is now set up. If we go ahead and combine these, and let's just go ahead and do that. So I have V1 times 1.5, 1.7 I think it is, yeah. 1.7 times V1 plus V2 times a negative 0.5 equals 10. And then on the second equation, we've got V1 times a negative 0.5 plus V2 times 1/2 plus 1/10 is 0.6 equals 2. And once again, you can now solve this either by elimination the way we did over here, or you can solve this using your matrix solver or using the solve function on your calculator. That part doesn't matter. You just need to figure out how you're going to solve these. So, node analysis always leads to fractions. How you deal with the fractions is up to you. When there's nice common denominator terms, least common denominator terms, you can eliminate the fractions and then solve. Or, as is more often the case, you're not going to have a nice clean common denominator. And it makes sense to just go ahead and combine like terms, deal with the fractions, and solve the equation. In both cases, you better find that V1 is equal to 100 over 11, which, you know, if you're working in decimals over here, you're going to get V1 then is equal to 100 over 11. That turns out to be 9.09. And V2 turns out to be 10.91.